So, as it says here, well, it doesn't say here, but we are starting integration for the next 3 weeks. Here are the success criteria for today. So, we'll develop the concept of integration, what it means. There's quite a few things to get through in this unit, so we're going to have to really push it to get there in time. But in today's lesson, we are simply going to examine the concept of the antiderivative. So you can see the success criteria there, and I'd like you to revisit that at the end of the lesson and see what you can tick off and what you can't tick off. So let's start off by doing a bit of a recall. So I can recall how to differentiate using the power rule. That's what we'll focus on to start with. Then we'll look at finding an antiderivative of a polynomial, expressing an antiderivative using integral notation. We'll do that in the second half of this lesson, and do some work on finding the indefinite integral. So that's the process we're going to take, but it's also what you can see as being the pathway to success for you for this lesson. If at the end of the lesson you can tick off most, if not all, of those dot points, then you can consider that a good lesson. And if you can't, then that gives you what you need to do next, right? That's all right. I'm going to zoom out so you've still got them there to write down if you want to write them down, but you can see what else we're doing for the rest of this lesson. So the tuning in activity there is one I want you to do right now. So we've got 3x squared plus 2x, and I've deliberately used capital F of x there. I'll explain why later. But so capital F of x is equal to 3x squared plus 2x. Can you find the derivative, please? In your workbook is fine. If the answer is no, I'll go through the answer in a second. Give you just under a minute to do that. Alrighty, that's my under a minute. So if f of x is equal to 3x squared, then you should have got f dash of x equal to 6x plus 2. Is that okay with everyone? If you got that, very well done. That's a good recall. And you can say, if you did manage to get that, that's basically that first dot point, really. You've differentiated using the power rule. If you didn't get it, 3 times 2 is equal to 6, and I decrease the power by 1, so it's 6x. X to the power of 1, 1 minus 1 is 0, so x to the power of 0 makes it disappear, and 2 times 1 is 2. I'm not going to dwell on that any further unless someone wants me to, but that's from our unit of work last year on differentiation. Awesome sauce. So antiderivatives are basically going backwards. So if I start off with little f of x equaling 6x plus 2, then we call big F of x the antiderivative, and it effectively means working backwards. So what would the function had to have been if its derivative was 6x plus 2? So big F of x would be equal to 3x squared plus 2x. So that's why I've got a therefore symbol there. And this one here, anyone seen that symbol before, the upside down triangle? So that one means therefore. I'm sure you know that. That one means because. Okay, f of x equals 6x plus 2. Big F of x equals 3x squared plus 2x because f dash of x equals f of x. Okay, big F dash of x equals little f of x. Wow, it sounds confusing, doesn't it? But you can see by the letters being used there what I'm talking about. I wonder what I'm going to write under the but there. Anyone got any sense of what the but might be? No? That's true as well, isn't it? If I find the derivative of f of x, if f of x were 3x squared plus 2x plus 1, that term would disappear, wouldn't it? Because the derivative of a constant is 0. Okay. So this bit here sort of denotes that there can be more than one antiderivative of a function. So there's not just one, like I've got here, 3x squared plus 2x, but there's an infinite number of antiderivatives. All of them are antiderivatives of this function, 6x plus 2. Is that okay? All right. So I want you to try this one. Again, in your workbook will be fine. And I want you to try to find the antiderivative of this function. So I'm going to call it f of x, and you need to find big F of x. 12x cubed minus 4x. Give that a crack. Really, just have to think about that one, that number. That's a very fancy F, Ollie. You might want to make them less fancy because they look a little bit like integration signs, which I'm going to explain a little bit later. I'm sorry to cramp your style. Looks like you've found the derivative, whereas I wanted you to find the antiderivative. Okay. Have a think about that last term. I know what you're going for there, though. Yeah. But not x, though. That's better. Okay. So if you had 3x to the power of 4 minus 2x squared, that's pretty good. If you had that. If you had 3x to the power of 4 minus 2x squared plus 1, you'd be right. Or if you had 3x to the power of 4 minus 2x squared minus pi, you'd be right. All of those would be right. All of them are right because it doesn't matter what that, well, we don't know what that last term would be. Hey, don't worry if you didn't get 3x to the power of 4 minus 2x squared at all because you couldn't work out how do we anti-differentiate. I'll go through it in a sec. But I guess the important thing to take away from this is that I hope it's okay if you accept that this, and I'll explain why later, is the direct antiderivative of this, as in without anything added on to the end of it, then I hope you can see that all the functions will have that at the start and then just something different at the end there. And pi, even though it's a symbol, is still a constant number, right? The value of pi doesn't change, nor does the value of 1, etc. So what I'd like to do is just express it generally. So generally, we use c to denote the constant term. So in general, we can write 3x to the power of 4 minus 2x squared plus c. And we use a capital C for it. And c just stands for the constant term, the term with no variables in it. We would avoid using, we can't use x because x is already used in the derivative. It's derived with respect to x, so we can't use x. Using y is a bit awkward. So c for constant term is the commonly used sort of thing. Okay, I am going to go through how we got 3x to the power of 4 minus 2x squared in a second. Any questions? Okay, I'm about to flip screens. Is that going to upset anyone if I flip screens now? Okay, so I'm going to develop this power rule, but I'm just going to start off with this example. And what I want to do, that we just did, is just sort of show you the thinking behind it, and then I'll write the rule down without much more exploration. So the rule makes sense, I think, but maybe just seeing it unpacked first might make it really solid for you. So we're looking at f of x equaling, it's the same as before, 12x cubed minus 4x, like so. And what we're going to do is we're going to see how we would build that up. Let's start off with a simpler function first of all. And I'm going to do that it's going to just be scratch space in slide 6 there. So if I had x squared, nice and simple, then if that was the derivative, then the antiderivative would have to be x cubed, because we have to increase the power by 1. Is that okay so far? Okay, well, if we're going to increase the power by 1, if I then go backwards, that would be 3x squared, right? But it's not 3x squared, it's just x squared. And so it would have to be, I would have had to have started with, a third to start with. So that when I bring the 3 down, my point is not working. When I bring the 3 down to here, it would cancel out with the third, leaving me with no coefficient, or a coefficient of 1. Intuitively, I'm hoping that might make sense, that we look at the power it needs to be, and we'll have to multiply the term by 1 over that power. So looking at the actual example, it would be like this. It would be 12 times a quarter x to the power of 4 minus 4 times a half x squared. So I'll just underline in red there that 4 and that 4 and that 2 and that 2. So the power rule for differentiation was to decrease the power. The power rule for antiderivatives is to increase the power by 1, but then you have to put a fraction outside, 1 over the new power. Okay, so if I just finish off that problem now, a quarter of 12 is 3, so we have 3x to the power of 4. Should have put the plus c there. And half of 4 is 2, so minus 2x squared. And then we've got our plus c. What do you think? Practice probably needed, but conceptually, is that okay? So we increase the power, but then we have to multiply the term by that fraction. So in general, I'm just going to squeeze it onto this slide. I think it would be okay. In general, if f of x equals x to the power of n, then big f of x, the antiderivative, would be 1 on n plus 1 times x to the power of n plus 1. Is that okay? I'm going to put a comma there. Whenever we put a comma there, it means we need to put restrictions or caveats on our statement here. What is our restriction here? Think asymptotes, think of all those things we do where we need to consider restrictions. What would be the restriction here? Sorry, Izzy? Yes. Izzy said n cannot equal -1. Because if n equaled -1, then this fraction here would be 1 over 0, which is an error on your calculator. In other words, you can't do it. Alrighty? So that means that the power rule for integration is covered for all cases except for 1 on x, because 1 on x would be x to the power of -1. And you might remember from your derivative days, when the derivative is 1 on x, what the original function was. Can anyone remember off the top of their head? No, unfortunately not. If it were, then we would be able to differentiate it, no problems. But it was actually something completely different. It wasn't zero, because the derivative of zero is just zero. It's completely left. You can't really sort of piece it together. It's just one of those things which you can learn. Close, really close. Was that you? No, who said E? Oh, sorry, Louis. Close. The derivative of e to the power of x is e to the power of x. Do you remember that? It was the natural log of x. So you're close with e. So ln x, the derivative of ln x was 1 on x. And so the antiderivative of 1 on x is ln x, the natural logarithm of x. So anyway, that's just we need to cover these cases, but that's not where I was going with this particular lesson. Okay, so we've got the power rule for antidifferentiation there, where we increase the power by 1, and then we multiply that term by 1 over n plus 1. And I've gone through an example. So what I'd like you to do now is I'd like you to crack open your textbooks, and for the next 15 minutes, I'd like you to try exercise 9A. And after we've had about 15 minutes practice with these ones, I'm going to just finish off the lesson by looking at integral notation and a few other things. So I'll pause the video and come back after then. Okay, so I guess one thing that's pretty clear to me anyway is that it's kind of a bit fudgy to be talking about little f of x and big f of x and so on. Makes me feel like I'm in a very high order episode of Play School talking about that. So we develop our own notation to talk about this concept of antiderivatives called integrals. Now, at its heart, integrating is the fancy term to describe antiderivatives, the process of finding an antiderivative. Having said that, though, that's a simplistic look at the concept of integration, because integration has a lot more to it, and we will unpack that as the unit unfolds, but I don't want to go through it right now because it's just going to make things a bit confusing. So in today's lesson, we're just looking at the notation, and then in a subsequent lesson, we'll unpack that notation more so. So looking at slide 8 here, so integral notation. Okay, so to find the antiderivative, we express the problem like this. I'll just use the same as the example up there, so 12x cubed minus 4x. And then we write dx after it. So I'll just annotate that. That's the integral of a function with respect to x. Is that okay? I might even zoom that up so you can sort of just see that in its awesomeness. Okay. Oh, I said anti-derivation there. I meant to say antiderivative. Like I said, this is a bit of a kludgy way of talking about it because it's a bit more than that. But that's basically what we're saying at this stage. To find the antiderivative, we use a big long S called the integral sign. Then we write the function in, and when there's multiple parts to it, we have to just put it in brackets, otherwise it won't make sense. If it's just like x cubed, then you don't need the brackets. And then a dx at the end says what we're integrating with respect to. So I say this, the integral of 12x cubed minus 4x with respect to x. Any questions about that? So I might do that on the next slide, and just go through, and it's exactly the same, really. So when we find the integral, we're effectively using anti-derivative techniques in order to find it, and then we put a plus c on the end. Now, there are two kinds of integrals. There is a definite integral and an indefinite integral. So this putting a plus c on the end of it is called the indefinite integral of the function. So I've just run out of room on this slide, so I just want to make sure you're okay before I move on. Okay, I will move on now. So the example is, I'll just do a simple example. Keep it simple, stupid. So an example would be, what is the integral of 3x squared with respect to x? Well, the answer is, we've got an x cubed, and then we would have 3 times a third, which would be cancel each other out. So we would have x cubed plus c. Okay, so this is called the indefinite integral. So rather than calling it the general form of the antiderivative or something like that and using little f of x and big f of x and whatever else, we can just say it's the indefinite integral. Any questions about that? Now, what I'd like to do is just briefly go through the different rules in regard to finding the integral. These are just the basic rules here. They are on page 293. So I'll give you a moment to find those. Now for the video, I'm just going to write them up on the screen. Oh, sorry, beg your pardon, I didn't realize it was all zoomed up. Here we go. So I'm just going to write them down as I see them in the textbook, but you don't need to because they are in the textbook. So write them down or not, it's up to you. So we're on page 293. So you'll see the first one there is just the power rule, as we've talked about before, but just with the integral notation. So the integral of x to the power of n with respect to x is equal to 1 on n plus 1 times x to the power of n plus 1 plus c. And again, we just put our caveat there, our restriction that n cannot equal -1. In the textbook, I just noticed it says n not equal to 1. That's not right. It's n not equal to -1. So just be careful of that from the textbook. If it's your textbook, you might even want to just modify it. Just put -1 there so it's right in your textbook. Okay. The next one is the constant rule. It's all fairly obvious in the sense that you've got the integral of k times x to the power of n for some constant k with respect to x is equal to kx plus c. Sorry, not x to the power of n, just kx is equal to kx plus c. And that should sort of make sense to you, I think. Notice that when we use like a constant like k, so it represents a specific value. We don't know what it is. That's why it's. Oh, sorry, I made a mistake there. My bad. I wasn't paying attention to what I was saying. There we go. Here we go. Try again. The integral of a constant with respect to x is equal to kx plus c. That makes more sense, doesn't it? Sorry, I was just away with the fairies there. So, which kind of makes sense again, because we know the derivative of, say, 10x is equal to 10 and so on. So it makes sense that the antiderivative would be kx. And I hope you can see with that little example there why it's kind of important to have the dot dx at the end with respect to x, because without the dx there, then you don't know whether you're finding the integral with respect to k. So the dot dx says k must be something constant in the function, and therefore the antiderivative, the integral of it, would be kx plus some constant c. Sorry about that. I just had a bit of a mind melt there. Okay, so the next one is what happens if I have a constant multiplied by a function with respect to x. Then we can effectively take the constant out and then just integrate the function with respect to x. So I'll just, maybe on slide 11, I'll just give you an example of that. Maybe I should give you an example of all of them except for that first one. So the integral of 7 with respect to x is equal to 7x plus c. The integral of 3x squared is equal to 3 times the integral of, with respect to x, dx, which is equal to 3 times a third x cubed plus c, which is equal to x cubed. A clunky way of saying it, but I'm just saying that's what it basically means. It means you can take the constant outside. The next rule is the sum or difference rule, which basically says that if I've got functions added up, then I can just find the integral of each one. So it's saying that the integral of f of x plus or minus another function g of x, and could you imagine that that could just naturally go to like 50 different functions if you want to. It just naturally expands, because g of x could be actually equal to k of x plus l of x, so it could go on forever. But when we find the integral of parts like so, then we find the integral of each part with respect to x, and that's a pretty important one, like so. And I haven't put the plus c at the end there because we haven't established what that integral would be, so there's no need to. All right, so an example of that one would be like maybe that other example we had again. What was it? 12x cubed minus 4x. So the integral of 12x cubed minus 4x with respect to x would be equal to the integral of 12x cubed minus the integral of 4x. Sorry, I forgot my dx's. Minus the integral of 4x with respect to x. And then that would give you, what is that? 3x to the power of 4 plus c. I'm going to put a 1 there, minus the integral of 2x squared plus c, which equals 3x to the power of 4 plus c1 minus 2x squared minus c2. Okay, are we right so far? I haven't quite finished this problem yet, but are we right so far? So all I've done is I've said it's the integral of each component. But, and this is a really important point, and you'll see it in the example we're going to go through in a second, that this C1 and C2, they're just stand-ins for any old possible number. So you don't need to have two of those things there. It doesn't matter. Okay, really all we're saying is that to this expression, 3x to the power of 4 minus 2x squared, we'd have to add something. So I end up by saying 3x to the power of 4 minus 2x squared plus c, no subscripts. Okay, I don't have to say C1 minus C2 or anything like that. I just need to say there is a constant term that's added to the end of it as well. Does that kind of make sense? Okay, so if you could please turn, well, if you haven't already, have a look at page 293. And I want to have a look at example 2C. Again, just for the video, I'm just going to put it up on the screen. And for you to look back at your notes as well. So it's the integral of 3x to the power of 5 with respect to x. So dx. Now over the page is the solution to that. So you can see that what they've done is they've taken out the constant. They've then just used a standard power rule. Oh, I better do it properly. Like so, and they put plus C1 there. They've then sort of simplified that out because 1 over 5 plus 1 is 1 over 6, and 3 times 1 over 6 is just a half. X to the power of 6 plus 3 times C1. So we're just using the distributive law to expand the brackets there. But you can see the last line there they've got in 2C is to then go, that's equal to half x to the power of 6 plus big C, like so. So in other words, it doesn't matter how complicated that constant is at the end, it's just a constant, and therefore you just express it with a C at the end there. So that's basically it. So I'm going to leave it there for today. Let's just have a quick flick back to the success criteria. So we started off by looking at this. I can recall how to differentiate using the power rule. I think you should be able to rate yourself on that one now. Find an antiderivative of a polynomial or a power function if you like. Probably a better way of writing it. The next one is express an antiderivative using integral notation. That's what we just had a look at, and you're going to have a bit of practice time for the last 10 minutes. And then find the indefinite integral of power functions n not equal to negative 1. So that's what you're going to practice now. So in 10 minutes time, I'm hoping you'll be able to look back at that success criteria and make a judgment as to whether you are feeling proficient or not. And if you're not, what are you going to do about it? So for the last part of the lesson, we are looking at page 294 and working your way through exercise 9B. And that will do us for today. I'll come around and help you.